Hi everyone, welcome to the special session of SPCOM 2020. My name is Rishabh Iyer and I'm an assistant professor in the CS department at UT Dallas. Today I'll be talking about combinatorial information measures with applications to machine learning. So I'd like to acknowledge that a lot of this work is based on joint work with an amazing set of collaborators. Aninat Khargaonkar, my student from UT Dallas, Himanshu Asnani, a collaborator from TIFR Bombay, who also actually is a speaker in this session, and Jeff Bilms from University of Washington. So the outline of this talk is that I'll cover, first I'll go over submodular information functions, then I'll go over a definition of these information measures, and then we'll actually go over some examples of submodular functions and the corresponding information measures. Then we'll go over some properties and finally cover a few different applications in machine learning. All right, so we'll start with what are combinatorial functions, right? And particularly set functions. So you have a set of items, basically a ground set, right? So this is a ground set of items, and amongst the ground set, I select a subset S, and each subset has a valuation f of S, right? So this is a number of applications in machine learning involve subset selection, right? Things like data subset selection and summarization. So functions over sets, right? To be a little bit more specific, we define f as a function from 2 raised to v to r. So given a ground set of items, you have a subset, right? And for every possible subset in 2 raised to v, you have a value associated with the subset, right? So general set function is very hard. So what are some special structure that we can exploit, right? So before getting into that, I'd like to point out a number of applications in machine learning involve subset selection, right? So ranging from selecting a subset of data points in machine learning for either labeling or for fast training, selecting a subset of images or sentences in document for summarization, selecting a subset of pixels in images, selecting a subset of features, frames in a video, etc., etc., right? So there are a number of applications in machine learning that involve selecting subsets of items. So a subclass of set functions that appear a lot in applications are the so-called class of submodular functions, right? So the main idea is that you have the notion of diminishing returns over here. So given a subset of items, we have two subsets, a subset of balls on the left-hand side and a subset of balls on the right-hand side. The left-hand side case is a subset of the case of balls on the right-hand side. We see that there is diminishing returns here, right? Because we add a blue ball, the gain in information, right? Or the gain in information here, where information is defined as a number of distinct colors of balls in the urn. Then this is actually a submodular function because the gain is 1 in the left-hand side case, but the gain is 0 in the right-hand side case, right? So continuing with submodular functions and the kind of intuition over here. So the notion is diminishing returns. So again, if you go to McDonald's, right, and you get a pack of fries, then you're probably not as likely to be thrown a Coke for free, right? But if you buy a fries and a burger, then you're probably going to be thrown a Coke for free. So again, this is diminishing returns in action over here, right? So there are two equivalent definitions of diminishing returns. One is the diminishing returns definition that we saw, that you basically add an element and the gain of the element grows as the context, the gain of the element shrinks as the context of the set grows, right? The second definition is known as a union intersection definition of submodularity, and many of you must be familiar with this from the entropic notions, right? So basically, the sum of the information functions over sets A and B is greater than or equal to the joint information with A union B and the information of A intersection B, right? So it turns out that both of these characterizations are exactly equivalent and both characterize submodular functions. A special class of submodular functions are so-called modular functions, right? Modular functions are basically functions where the cost associated with the set is additive across the elements of the set, right? So from a diminishing returns perspective over here, the gain of adding element E is independent of the set. So you have a subset or the superset. The gain is always WE, which is the weight of the element or the cost of the element E. Another notion is monotone functions, and monotone functions, set function is called monotonic, if as the set grows, as you have larger and larger sets, the value increases as the set grows, right? An example of a monotone function is entropy, right? So the second example over here, you take entropy of a set of random variables. We actually see entropy when we talk about information and submodularity, but it turns out that entropy as a function of a set of random variables is actually a monotone function as well. All right, so now let's get into really why, if you saw the title of this section, I said submodular information functions, right? So why are submodular functions natural kind of information functions? So to kind of see this, let's look at concrete example of basically kind of understanding the information contained on a set of images, right? So I have two sets of images, one which is a superset and a smaller set with a subset, right? You can define any notion of an information function, right? Think of it like, for example, the number of concepts that are covered, right? Or basically how similar are basically pairwise similarity between images, right? So you can think of any information function that measures the information content of a set of images. Then most natural information functions would satisfy this property, right? The property of diminishing returns. So you add a new element here, the gain in information of the new element would be larger in a smaller set as opposed to a larger set, right? So this is again diminishing returns as the context of the set grows. This is an information function. To kind of be a little bit more concrete about information functions, we can actually define entropy, as I mentioned a few slides back as well, can define entropy over a subset of random variables, right? So I'm given a set of random variables x1 to xn, and I choose x of s, where s is a subset from 1 to n, right? And I define the joint entropy of the variables indexed by the set s, right? So this quantity is actually a submodular function. And not just that, it actually turns out that it's a monotone submodular function, right? Which is a special class of submodular functions. And the proof of that is very, very simple, right? So the proof of that is that information never hurts. So you have basically the entropy of x of e given b. This quantity shrinks as the context of the set grows. But beyond entropy, right, there are actually several different subclasses of submodular functions, and we'll actually kind of review a few of them over here in this talk, right? So the first class of submodular functions is the so-called representation functions, right? The second is coverage functions, and the third is diversity functions. So we'll actually go over these in the next few slides. The first is representation functions, right? So given a set of data points over here in green, the representation functions basically capture how well does my subset represent the entire set, right? So if you say I have a subset of points in red over here, we can say fairly confidently that this set actually represents the entire green set pretty well, right? So an example of a representation function is the facility location, right? Facility location is a representation function. There are a few others as well. In some sense, representation functions are very similar to k-medioids in clustering, right? So they are equivalent to what a k-medioid clustering would try to do. The next notion, which is different from representation, is known as diversity, right? So diversity means I don't care about how well my points represent the entire set. What I really care is that my points should be as different from each other as possible, right? So this is diversity. An example of a function is a log determinant. This is again a submodular function. Third class of functions is the coverage functions, right? Here I'm given a set of concepts, and each of my document or say an image covers certain concepts, right? And I want to basically measure the information content of a set of either documents or a set of images, and I want to measure this based on the set of concepts that are covered, right? So this is again a submodular function. This is so-called set cover. All right, so having kind of seen carefully a number of kind of submodular information functions, looked at a few examples of submodular functions, seen why in some sense they should measure notions of information, we kind of define this a little bit more concretely, right? So to do this, let's recap and look at the kind of information theoretic or rather entropic notions of information, right? So given a set of random variables x1 to xn, entropy of the subset of random variables is defined as h of xa, right? And it's defined in this way. Similarly, basically having seen entropy, based on entropy, now we can define many other information theoretical quantities, right? The first is mutual information. So the mutual information between two sets of random variables. No, typically you have seen mutual information in two random variables. You can actually extend this to mutual information in two sets of random variables. So I'll just define the more general term over here. The mutual information in two sets of random variables is the entropy of A plus the entropy of B minus the joint entropy between A and B, right? The third quantity is conditional entropy, and the conditional entropy is basically the entropy of x of A given x of B, right? So it's the joint entropy of A union B minus the entropy of B. Finally, can also define the conditional version of the mutual information, right? So I'm given sets A, B, C. I have the conditional mutual information between xa, xb given xt, and this is h of xa given xc plus h of xb given xc minus the joint entropy between A union B given xc again, right? So in terms of the conditional entropies, you can define the conditional mutual information. You can actually expand this to other forms that are probably more well known, but I'll just stick to this equation, right? So these are four very well-known quantities, and you can kind of further generalize upon these quantities as well, right? So I'll kind of now get back to entropy and actually talk about what makes these really information functions, right? So Shannon, in all of his wisdom, he kind of came up with certain very fundamental properties of the entropy functions, right? And these properties are first, that it is normalized, right? So f of the empty set is 0. So if I have no random variables, the value of the entropy is 0. It's monotone. So as I add more random variables, information only grows, right? So it's a monotone function. And the third property is a so-called what he called the two alternative property, which actually is nothing but submodularity. So it's f of A, the joint entropy of A plus then the entropy of B is greater than the entropy of A union B plus entropy of A intersection B, right? But what is very interesting is that these three properties, right, actually kind of show the non-negativity of many other information measures as well, right? So property 3, in fact, can be shown to imply the non-negativity of the mutual information and the conditional mutual information. So both of these are non-negativity just thanks to property 3. And properties 1 and 2 actually imply that both the entropy and the conditional entropy are actually non-negative. So this is great, right? But the definition that we saw, the so-called Shannon inequalities, actually hold for a much broader class of functions, the so-called Poly-Matroid functions, right? So the Poly-Matroid function f is a set function which actually satisfies these three properties, right? So in fact, they are normalized monotone submodular functions. And an interesting observation is that these Poly-Matroid functions actually generalize entropy, right? So kind of having seen this now as a kind of even a tighter connection, we can define now the submodular information functions, right? So I'm defining the kind of so-called information function, which is nothing but the submodular function over a set of data points A as f of A. Note that I'm not assuming really that my set of data points are random variables. They could be deterministic set of points, right? So given a set of data points, given a set of images, for example, or given a set of documents, or a set of data points for machine learning, I want to basically kind of define some notion of information. Right? So I can kind of, if f is a Poly-Matroid function, I can say that this is a reasonable notion of information of a set of data points. Now, given this, I can define the submodular mutual information. Right? So this quantity is the mutual information between A, comma B. This is f of A plus f of B minus f of A union B. Right? So this is great. We have the mutual information, and again, if f is back to the entropy function, this is basically the standard mutual information, right? Can similarly define conditional gain as the gain of adding a, basically the gain of a given b, right, as f of a union b minus f of b. And finally, you can define the conditional mutual information as basically this quantity. Again, very, very similar to the entropic notions we saw before, right? So what's the intuition of this, right? So submodular information is kind of clear from the name. The submodular conditional gain is the gain in information of adding a set A to a given set B, right? The submodular mutual information is in some sense the joint information between sets A and B based on it, right? So it's essentially how similar are A and B, or is the joint information that both of them contain. And finally, the independence is essentially the notion of minimal mutual information, right, or minimal joint information between two sets. So these are two maximally different sets based on F. So very interestingly, right? Submodular information functions actually are a subclass of the entropic, or actually a super class or a superset of the entropic class of functions, right? So this was shown by Zhang and Jung in 97-98, where they actually showed that certain inequalities actually only hold for the entropic quantities, right? So the entropy. So if this is the entropic mutual information, then this inequality actually only holds for the entropic mutual information, but does not hold if you just assume the Shannon inequalities, right? So that means that there are submodular functions where this inequality does not hold. In fact, similar to this, there are actually several more, in fact, a large number of infinite number of inequalities that can be generated that entropic functions satisfy that submodular functions don't satisfy, right? So this kind of begs the question then that how do we kind of characterize these functions? So it turns out also that, for example, set cover and facility location and Matroid rank, they do not satisfy these, right? So in some sense, these are kind of broader classes of functions. All right, so basically given this notion, again, we can define independence between sets, very similar to the entropic notions. I have two sets of random variables. If the mutual information is zero, they are independent. Similarly, the conditional mutual information is zero, they are independent, right? There are actually, turns out there are certain properties. I'll actually skip this in the interest of time. You can also define multi-set submodular information quantities as, and we define two specific information quantities, the total correlation and the multi-set mutual information between k sets, A1 to AK. I'll not get into too much detail over here, but it turns out that these also are actually applicable in a number of applications in machine learning, like clustering, etc. So we very quickly, I'll go over one example of basically the mutual information in 2 and 3 dimensions, right? So when k is equal to 2, this is the mutual information between two sets. A over here refers to the conditional gain of A given B. The small b over here refers to the conditional gain of B given A, right? And C is actually the mutual information between A comma B, right? So there's a kind of a nice Venn diagram representation in the case of k equal to 2. We can also do this in the case of k equal to 3, right? So the quantity A over here, which is basically this notion, so it doesn't involve any of this, it's just this, is the information content in A that is not in B and C, right? So we can basically define this as A given B union C. Similarly, you can define B and C. It turns out that D, right? D, if you see D plus G, this entire region, this is the mutual information between A and B, right? So essentially, D is the mutual information between A and B, but subtracting out C, right? So this is exactly the mutual information between A comma B given C. So this is the conditional mutual information that we saw, right? So similarly, D, E, and F are variants of the conditional mutual information. And the quantity G over here is actually the kind of multi-set mutual information between A, B, and C. So this is kind of a very interesting characterization of the submodular information. All right, very cool, right? So now let's actually kind of instantiate this for a few different set functions and kind of we can see some nice properties, right? So we'll start with the simple modular functions. Note that actually modular functions are a subclass of entropic functions because if the set of random variables are independent, jointly independent, right, then in some sense the function is actually additive or a modular function. The entropy function is additive, right? So f of A is W of A, f of A given B is W of A minus B. This is a set difference, right? The mutual information is W of A intersection B, right? And two sets are independent if they are disjoint, right? So this is basically all of this kind of follows kind of intuitively by looking at the entropy and looking at independent sets of random variables, right? We can take this one step forward and look at weighted set cover, right? So define gamma A as the set, the kind of covered set of A, right? So f of A is the weighted covered set, weighted set cover. F of A given B is nothing but the weighted the weighted version of gamma A minus gamma B, right? So there's a set difference in the covered space. Similarly, the mutual information is actually weighted version of the intersection between the covered sets of gamma A intersection gamma B, right? And similarly, independence is basically two sets are independent, not necessarily they are disjoint, they could be disjoint, right? But we require that they cover different concepts. So there is no concept that is shared between A and B. Again, this is something that is very, very intuitive if you look at it from a set cover perspective, right? I'll skip facility location in the interest of time. You can also define this for penalized sum coverage. What is interesting, I like to point out over here is that with this function, it turns out that this is exactly related to the cut function, right? So the mutual information is basically the cut between sets A and B. And in fact, if you look at the mutual information A comma B minus A, this is exactly the graph cut, right? And two sets are independent if the cut between the two sets is 0. Right? So again, very intuitive way of capturing mutual information over here. You can also define kind of the probabilistic version of set cover, and you have certain intuitive quantities from this. I'll skip this, in the interest of time. Let's talk about some basic properties of some of these information functions, right? So the first basic property is non-negativity. A lot of this actually follows, kind of straightforwardly if you assume that f is a Poly-Matroid function, right? So the first is non-negativity. We actually saw this in the kind of Shannon inequalities and the entropic concept. So just because f satisfies all the Shannon inequalities, naturally each of these entropic quantities, or actually in this case, Poly-Matroid information quantities are all non-negative, right? So this is kind of straightforward. It also follows, because of the Shannon inequalities, that you can actually show that these are monotone. So, well, it's basically by definition that f of A and f of A given B are monotone, right? But it also turns out that I f of A comma B is monotone in A for a fixed B, right? Similarly, the conditional mutual information is again monotone in one of the sets A for a fixed B and vice versa. By the way, it's kind of obvious that the mutual information quantities are symmetric. So you can kind of flip A and B and you have the same properties in A and B, right? So there is a symmetricity property, which is basically just by definition. Finally, you have these upper and lower bounds. All of these also hold for the entropic notion, so they are somewhat straightforward again. You have f of A given B less than or equal to f of A, and similarly the mutual information is bounded by the information content of the intersected set A intersection B and the minimum of f of A comma f of B, right? So this is basically, this kind of lies in between the two, and so on and so forth, right? So you can also define this for the conditional mutual information as well. All right, so what is actually very interesting that we actually found out is that mutual information also has a certain submodularity property. And to get to that, I'll actually take a slight detour and again recall that monotonicity, right? Monotonicity is basically equivalent to first order partial derivatives being non-negative. Right? So what is the first order partial derivative is nothing but the gain of adding I to A, right? So it's f of A union I minus f of A. Submodularity is the second order partial derivatives, right? Which is I comma j given A, right? Which is basically f of I given A union j minus f of I given A. This quantity should be non-negative, non-positive. Then it's actually submodular. So this is very akin to concavity, right? Concave functions have basically second derivatives being non-positive. However, you can define an additional requirement on certain submodular functions that if they satisfy the third order partial derivative being non-negative, right, which is this quantity Fijk given A being greater than or equal to 0, then this subclass is interesting. It turns out that actually the set cover, facet location, concave over modular, etc., functions, so actually quite a few functions satisfy this property. But even certain very simple functions like the uniform matroid rank function actually does not satisfy this property for a certain subset. For one particular subset, it does not satisfy. So this is actually very interesting, right? Because what it means is that given this kind of subclass, we can say some interesting things, right? And precisely the interesting property of this subclass is that it is related to submodularity of the mutual information. So before getting to that, note that the submodularity of the f of A and f of A given B basically follows from definition, right? But the submodularity of if of a comma b is actually not obvious at all. And it turns out that if f satisfies this property, then they are both submodular. However, in general, they are just a difference of submodular functions. And so this is what actually makes this interesting and amenable to applications and optimization problems. So, all right, so now actually we can move on to a few different applications. So I'm actually not going to cover a lot of experimental results, again, in the interest of time, but I'll cover the main ideas of the applications, right? So in some sense, this is a framework of applications that applies to summarization, data selection, recommendation, search, etc., etc. Right? So a large number of applications. You select a subset of data points for machine learning. You select a subset of either images or documents for document summarization, news summarization, image collection summarization. You want to recommend a set of movies to users in Netflix. You want to recommend a set of products or items in Amazon for search. I mean, at Amazon.com, right? So basically, all of these are kind of summarization / data selection / recommendation applications. What is common in all of these is that they require some notion of diversity or coverage or representation, right? So you would need some notion of a submodular function for many of these applications, because you don't want to just select, you don't want to show the same redundant set of items to users. You want some kind of diversity, right? But you also want to do this along with some notion of query relevance, right? So if it's a recommendation system or a search, you have query relevance, but you also oftentimes have privacy requirements, right? So there are certain contents that may not be applicable to certain users, or there might be certain content that you don't want to show in a summarization application, right? It's personal details that you don't want to, personal images that you don't want to have in the summary that is shown outside. So having a summarization framework that kind of has all of these is actually very important. So we shall actually present a unified framework of data summarization, and this unified framework will actually use the information functions, right? So the basic framework is without any query or privacy restrictions. You just maximize f of x, right? So f of x is the information content. It could be some kind of coverage plus representation plus diversity, right? You maximize this, you get a summary, and so on. This has been studied in several papers. The second is when you add one restriction on top of extractive, you want to make it related to the query, right? So you can pose this as maximizing the mutual information based on f of x comma q, right? So this is again an optimization problem that involves the mutual information. Now the third layer is that, okay, I don't care about the query, but I care about privacy, right? So I can pose this as maximizing the information of f of x given p, right? And fourth is where I have both query and privacy. And in that case, I want to maximize the conditional mutual information between x comma q given p. So actually what is interesting is that this kind of subsumes, this formulation unifies all of this, right? So when my query is everything, that is, I really don't have a query, then if of x comma q given p is essentially f of x given p, right? So this is privacy preserving summarization. If my p is empty, so there is no privacy constraint, then if of x comma q given p is basically if of x comma q, right? And when I have neither privacy nor query, right, then this is exactly f of x. So I get back the extractive summarization. So essentially, this is the kind of unified optimization problem that we probably care about. And we get these cases, right? And the main result is that when f satisfies this nice property that the triple partial derivatives are non-negative, then this function actually is a monotone submodular function, and we can actually solve this using an approximation guarantee, right? All right, so very quickly in the next 30 seconds or so, I will summarize some future directions, right? So the first is extending a lot of the kind of multi-set properties, multi-set total correlation, multi-set mutual information, like the multivariate mutual information, and kind of using these for multi-set kind of property or multi-set optimization problems, right? For applications like clustering, where you want to select k different sets of data points, or diverse partitioning. The second aspect is actually to learn some of these submodular information measures, to use them in machine learning, right? So in a diversified summarization case or a recommendation system, you actually want to learn the models given data, right? The third is kind of understanding subclasses of submodular functions and their connection to entropy, extending notions like distance metrics, generalized entropy, directed mutual information, etc. And finally, kind of extending stochasticity in this framework, right? So that's great. Thank you so much for your attention. And I'll actually end over here. I'd like to take questions at this point. Thank you.